Okay, wonderful. So as people are trickling in, I think I'm just going to get started because the first slide is more of an introductory slide. So I'm going to lay out the plan for today. It's actually a lot of material. One of my favorite topics, traits in Rust. Traits are super cool. They're super exciting, but they're really weird when you see them at first. So please ask questions. We'll also be talking about generics. I think these two topics go hand in hand because there's a lot of interesting ideas about generics in Rust. So by generics, I mean like, you've already seen this before when you have like a vec of U32 or a vec of string. It's like, how do I take this one type? How do I make it a generic container that can hold anything? And you might have seen this in other languages as well. You probably even saw it in CS 106B. Maybe even in 106A, if you saw the Java version when you had like array lists and stuff like that. And if time permits, I would love to show you an example in a real world system, in an embedded operating system called Talk, where you can actually see really cool examples of traits at play in very low level OS kernel code. And the next time, this Thursday, we're going to be wrapping up traits and generics, and we will be discussing smart pointers, ideally. So just trying to make it kind of like adaptive based on how far we get today. So I'm going to keep an eye on the time. And then next week, Ryan's going to be talking about multiprocessing pitfalls and some interesting components of multiprocessing in Rust. Like for instance, like, what sorts of like constructs does Rust have to support like communication and stuff like that, especially in like signal handling. So that's going to be super interesting. And then I'm going to be switching a bunch between slides and code during this because I'm going to be like sort of like live coding a little bit as well. Hopefully that doesn't incur too much overhead, but we will see. Please ask questions. Just making a point of this because this is like tricky material, I think, especially with the traits. Otherwise, I'll just happily like march forward in the slides, and then maybe like people will be confused for a while. And when you're asking questions, please unmute yourself. I can't necessarily see what's going on in the chat. And if you have a question, other people probably have the same question. And I'll just try to go like adaptive based on that. I can also look for hands when I pause for questions, I guess. I guess you can indicate. Oh, I see something in the chat already. Let's see.
That was me. I just said happy to answer asynchronous questions.
Okay, great. Oh, whoops. Now, okay, so the Zoom does this thing, I think, because like when I'm in full screen mode, here, I'm going to stop my share and I'm going to start it again because Zoom is strange. When you're in full screen mode, it's hard to click on things. And when I'm presenting, I'm in full screen mode. So that doesn't work well. Oh, sorry, Dad, I'm lecturing right now. No worries. It's all good. Yeah, it's just a very typical spring quarter 2020 thing right now. Great. Okay, thank you all for bearing with me. All right, so y'all can see that again, right? Okay, lovely. So we're going to present it again. We're going to go back here. Yes. Actually, on that last bullet point, please just unmute yourself if you have a question. I think it'll be much easier for me, especially if I'm in full screen mode, as we just saw. Great. So now we're just going to be going into the actual material. So let's talk about grouping related functionality together. So you've probably seen this already in C++ and in Java, right? So on the left-hand side, we have some C++ code, and we have, you've got this abstract class shape, and you're saying, I have this thing that's a shape, and what are certain qualities of a shape? Well, it has an area, it has a circumference, and we can like get a description of it. And you'll notice those are defined as like virtual methods, like the virtual equals 0 method. That just basically means that you can't instantiate a shape itself. It's an abstract class, but this is kind of describing an interface. Like what defines shapiness? Okay, shapiness means having an area, having a circumference. Oh, I guess maybe this is particular to a circle or something, right? But then I will instantiate something like I'll instantiate something that inherits from that abstract class, like maybe a circle, and I'll implement the actual area and circumference examples. Functions. Does that make sense to everybody so far? And on the right hand side, you have an example of something. We have an implementation of an interface in Java. So I don't know if y'all have seen interfaces in Java before. Completely fine if you haven't. I know like recently 106A hasn't been in Java, and maybe even when it was in Java, they might not have even gone over interfaces. But just in case you've seen this before, an interface defines, what functions does a class implementing this interface have, right? So for instance, we have this player class, and it's implementing comparable. And that means I can define a compare to function on this. And the nice thing here is that if I define, say, an array list, right? That's just the Java speak for vector, right? An array list of players, I can sort them because they implement this compare to function. and sorting is comparison based. Are there any questions so far? So this is sort of just like setting the stage for like the kind of functionality we want in Rust. And the way we get this in Rust is we use this construct called a trait. So they sort of define, what can this type do, right? So this was at the very end of the lecture notes last time. If there was enough time, I would have gotten to it, but there wasn't, which was fine. But you see that like one of the examples that we'll see in the next slide is, there's this display trait, right? So this is saying if a type implements the display trait, it knows how to show itself in a certain sense. So that means if I do like println of like the empty curly braces, which is just like a formatter of this type, then it will print itself in some nice way, right? So if I define a point and I implement display for it, then I can like describe like the XY coordinates of it or something like that. I can also define how do I copy this type, like is this a type that I can clone? Can I make, and also like if I implement copy, that changes the semantics of that equal sign operator. So we actually saw this the very first lecture. We started talking about ownership, right? So the integers were kind of funny because they kind of broke the rules of ownership in a sense, but they're not really breaking the rules. It's just the assignment operator means something different. Instead of transferring ownership, it means copying it over. So that's what it means to implement the copy trait. Sometimes these traits, as we'll see, can overload operators in a sense. So in this case, this is like overloading the assignment operator. Instead of the assignment operator transferring ownership, it will make a copy. Does that make sense to people? Can I see like maybe some nods? Like the couple of people who pop up in my little like Zoom minified window. Yeah, it's one of the additional struggles. Also, iterators. Iterators are a great trait. You'll see this in the exercises. So clone and copy. So you'll definitely see clone in this week's exercises. And converting, like, so we defined this wonderful linked list last lecture, right? How can I make that linked list play well with Rust iterator syntax or something like that, right? Like how do I do like a for loop over it, and how does Rust know what that means? So we do that using traits as well, and also equality. So this goes back to how do we define comparisons between things? How do we overload the equals equals operator and the not equals operator? So sometimes we want to override functionality. We'll see this in like overriding the drop trait in our lecture example. We'll see deref later. That's so like what is it? So this is kind of funny. Like we're sort of like overriding what it means to like dereference something. I'm not going to talk about that too much today. When we talk about smart pointers, hopefully this Thursday, we'll talk about that much more. And then it also allows us to define default implementations. So like with toString, we'll see how if something implements display, we can automatically implement toString for it, because display works with like a buffer. And what I can do is I can create some sort of like string buffery type thing. I can write to it, and I can just return that string. So these are very powerful, flexible ideas. This is all very abstract, by the way. I haven't shown you any code yet. I'm going to show you code really soon. Also, the last point, overload operators. So if I want to define addition, like if I had like an XY like Euclidean plane point type, and I wanted to define what does it mean to add 2 points, or if I had like a vector of numbers, what does it mean to add 2 vectors, I can overload these operators too, and that's also super cool and exciting. Any high-level questions right now, or any like confusion that people have already? Okay, so moving forward, so let's look at the linked list traits again. So I'm going to open this link. I think, okay, I'm actually, so you can't even see that screen, so I'm going to stop the share and I'm going to start it again. Hopefully this context switch doesn't take too much. Great, do people see that? Okay, lovely. So this, if you have the slides, you can even follow along if you'd like, and you can see this is exactly the same example we had last week, except I took out the display function. We had this display function that we used for debugging, and what I did is I'm using this syntax right here. I'm implementing format display for the linked list. So just like take a quick look at that, digest that for a moment, the thing I have highlighted there. So just to parse this a little bit for you, first of all, I'd like you to ignore some of the funky syntax here. So it's returning something like a format result. Like, don't worry too much about what that type means. Also, there's this like funky syntax here. Don't worry about what that is either. The reason I'm showing you display as opposed to toString is that most people, like the Rust documentation suggests not overriding toString or not defining it yourself. You should define display, and toString you'll get for free from display. So don't worry about like what this formatter is. just think about this F as like a buffer. This could be like a file buffer, or like some sort of like file descriptory type thing. This could be like, some sort of like input some sort of like socket you're writing to, like we don't even like really know. It's some sort of like formatter object, right? That will format things and pass them to something that can handle that text data, right? Um, and what we're doing here is we sort of just, right, so we're just going through each of the nodes and we're updating a result. We have a result that starts out as an empty string. So so this is exactly what we were doing before. We started this result out as an empty string. We're going through the nodes. We're using this match statement syntax to look at the current node. We're saying like it's either a node or it's like this none value, which is like our null pointer. I'm going to update the result using this format bang macro. So this is sort of, you might have seen this in Hangman. This is essentially, it's sort of like println, except instead of printing to your console, it returns a string. And then I'm just going to march on to the next node. So we don't have to think too hard about it, I think, like the linked list logic here. But like the important thing to take away is that we have this result that starts out as an empty string, we're adding to it, and we're writing the empty string to this buffer. And now the magical thing is if you look down here, I no longer have to call display on the list. Take a look at this. This is so exciting, right? I can println, the empty braces here, this highlighted line, I can just print the list out like that. It just knows how to show itself to println. So if I run the code, you'll see, okay, it's taken a while, but you can see that it shows the list just fine, right? So it's able to, so we pushed everything to the front of the list, and then we're able to show, so that println corresponds to this line here. So that's the magic of display. Display kind of like redefines the meaning of like, what does it mean to print this data type? Does that make sense to people? Are there any questions?
Can you scroll up to where the thing is defined? So for anyone confused, impl format : display means implement the format display trait for the struct that we defined.
Exactly. And this is, and in the, later on we'll see how we define the traits, but the definition of display is saying that like you have to define a function with this prototype. Thank you for making that point. I kind of just blasted through that. Does that make sense to people? So it's saying like this format function is a required function, and that's something that you just kind of have to do. And then for this linked list, I'm going to give you this particular linked list specific implementation of it. The next thing I want to talk about is drop. So this is actually, so drop, we see an implementation of it right here. This is very slick syntax. So I actually took this from, there's this interesting like series of examples. It's like learning Rust with entirely too many linked lists or something like that. But they wrote drop in this really slick way using this for loop syntax, where this is kind of like another example of like fancy syntactic sugar for error handling. You can do this thing where you can in like the conditional of your for loop, you can say like, I'm going to try to match the current node to sum. If it matches to sum, then great. I'll kind of capture it within this node. If it doesn't match, then the while loop is kind of going to break in a way. So yeah, I mean, if there are any questions about that syntax, please let me know after lecture, because I don't want to focus too much on the syntax. But it's sort of just like another, like if you're reading Rust code, this is something that you might be able to see in terms of error handling. A conceptual question I want to put out there is why might I want to implement drop for linked lists, right? We were just talking to you about how great Rust is in terms of automatically managing memory for you. And it's fine. If I just commented this out, it would be completely fine and it would totally deallocate itself. But can someone maybe like propose a reason for why we might want to override it? I'll give you a hint. It sort of had to do with last week's assignment. It was something with print diff, how it was defined, and how we told you to, we said a better way of defining it would be. It's kind of a tricky question. It's kind of a weird point. Any like random thoughts? So, like what was yes. Yeah, so it's exactly about efficiency, right? So that's a great point. Sorry, you're kind of like breaking up there a little bit, but it's that's exactly right, Ian. It's about efficiency. Why is it more efficient to do it this way? Like, what would the default implementation do? I guess, yeah. Yeah, it's kind of unfair of me to ask y'all because I'm trying to because we never explicitly talked about it. But what happens is drop kind of gets called recursively for each of like the structs. So like what would happen here is if we didn't override our own, like we would recursively call these drops, and if we had a giant linked list, we could just totally destroy our stack. Some of you might have seen this in the last week's assignment if you just decided to do print diff recursively because this is not like nice and tail recursive. The compiler can't optimize it away. So that's why we might want to override the default functionality like this. Does that make sense to everybody? Are there any questions about that? Right. So that's a great question. So what does dot take do? Dot take will yeah, so we sort of talked about this last week. It will convert that mutable reference into, because like what this unpacking here does is it gets like a mutable reference to the node. So it'll take the mutable reference and it'll convert it to an owned type, right? So this is an owned type that now contains this box, and in order to get that box to deallocate, so remember the box is a pointer. So if we, sorry, let me just go up to this definition here. Right, it takes an ampersand mute node and it gives us one of these structs. The struct contains a box, right? A box is a pointer to heap memory. In order to get that heap memory freed up, we need to like essentially uh, like take ownership of it, right? We take ownership of it here with current, and then notice how current goes out of scope by the end of this curly brace, right? So once current goes out of scope, the box will deallocate its heap memory. It'll call free. We'll talk about like those like smart pointery type things on Thursday, by the way.
Another way of thinking about it is it moves something from the struct to your variable. So if you do self.head.take, it's moving the box out of self.head, out of that struct, and into your current variable. And then you do some stuff with it, but then on the next iteration of your while loop, current gets replaced with something else, and the Rust compiler is like, oh, current, like the previous value is no longer being referenced, is not accessible anymore, and so it'll free that memory.
Yeah, actually, I think yeah. What I should have said was this is technically where it goes out of scope, where we overwrite it here. Um, Not because like currently it was still holding on to it here, but then like once we overwrite the value here, then it no longer has access to the old value. Then it goes out of scope. Then it gets freed. Yeah, it's a great point. Um, so, but yeah, notice we have the same impl drop for linked list. So the syntax is always impl trait name for type name. There's like the syntax. So I think yeah, what I wanted to get through this first example is just like the general syntax, the idea of a trait. Does that make sense to people so far? Are there any ideas about just traits, like what they are, like at like first order? Okay, so then we're gonna go back to the presentation, and the next thing we're gonna talk about is deriving traits. So what deriving traits does is actually, sorry, I have to share my screen again. Lots of context switching. What deriving traits does is it provides us with reasonable default implementations, right? So it's common to do this with things for equality, so like EQ versus partial EQ, copy, clone, debug. You might be wondering, what's the difference between equality and partial equality? This is a very technical point. So I don't know if you remember from CS 103, if you've taken CS 103 yet, but an equivalence relation satisfies three properties. It's reflexive, which means A is equal to A. It's transitive, and it's symmetric. So if A is equal to B, then B is equal to A. So a partial equivalence relation is something where you take away the reflexivity of it. So you no longer have to have that everything is equal to itself. And for F64, which is the float type, this is essentially the same thing as double. You have that not a number is not equal to not a number. This is kind of a funny like philosophical point, I think. But like this is just like some like technicality that we'll need for when we're defining our point type. So we'll see the point type pretty soon, and we'll we'll need to derive partial equivalence for it because the F64, which is inside of the point, doesn't give us full equivalence. But the cool thing with traits is sometimes you don't even have to go through the trouble of like defining it yourself. Sometimes the Rust compiler can say, hey, this is a pretty simple struct. I think I know what to do here. And you can sort of just trust it. So we're going to see that really soon. So that's called deriving traits. Over here, I've provided a list of all the things you can derive, just like a handy dandy list right there. This is taken from the Rust book. But let's look at another concrete example because I think it's much easier to understand these things with concrete examples. So we're going to switch over again to another code example. So can you all see this? Great. So notice here how I don't have any impl traits. I don't have any impl trait something for point. I just have this line up here. So I just want you to digest that line. This syntax basically means I want you to derive debug, partial EQ, clone, and copy for my point. Okay, so let's go through each of them. Debug means I know how to show the point in a debugging context. It's very similar to display, except you have to provide a special formatting string to show the debugging version of it. And the formatting string is, I've highlighted it here, it's like this funny like curly braces with the colon question mark in it in order to show the debugging version of it. So this will let us see our points when we're trying to debug our code. There's partial equivalence defined on it. So the way this works is it'll say 2 points are equal to one another if and only if their struct members are equal to one another. And the reason this works is because these struct members, they are F64s, and F64s have a notion of partial equivalence already. So it knows exactly what to do to compare 2 points together. And then in terms of clone and copy, it sort of does like the logical thing as well. In order to, because these F64s implement clone and copy, or because they implement clone, you only have to implement clone in order to implement copy. Because the F64s implement clone, we know how to implement clone for the point. And because we can clone the point, because we can make, like duplicate versions of this point, we can implement copy for it, which will override the assignment semantics. Sorry, that was a lot of information. Are there any questions? I'm going to pause for questions. Yes, Warren. Precisely, that's exactly how it works. It goes directly above a struct. It's a great question. Any other questions? That's a great question. So the distinction is for clone, I have to be explicit. So like vector, for instance, or like string is a great example. It implements clone. I can say like if you have a string like ABC, I can do like s.clone, and that'll give me a fresh string that has the same contents as what I just cloned. But copy is overriding the single equal sign. Copy is overriding what it means to do assignment. So previously we would transfer ownership. So like with strings, by default, we're always transferring ownership with that assignment operator. But remember with integers, or like things that are like smaller especially, we will be actually creating a copy. So we'll actually see that in the example right here. So that's a great segue. So if you see in this example, I implemented point here using our favorite syntax. So this impl point, this is like implementing the object, right? We're not implementing a trait for it. This is how we define a new point. And then as you see here, if I set let the origin, so this is fine. So let the origin, this is equal to a new point. If I have p is equal to the origin, right? This copies over this other point. So these are copy semantics here. So copy semantics, do you see I highlighted there that equal sign? Copy semantics redefine what that single equal sign means. That's the way to think about it. And then here I can show you, notice I also derived partial equality for them, right? So I show you, it's like, here's the point and the origin. Are they equal? This like makes sense, right? And then I can add 10 to p.x, and we can compare it, and they're going to no longer be equal. So if we just run this example, you can see that exactly there. So these are how the points start out. I can show them like this because I derived the debug trait. Let me actually show you. What if I like took away a couple of these things? Like if I took away debug, what's going to happen, right? Point does not implement debug. Sad, right? Let's see. But okay, this is one of my favorite things about the Rust compiler. It tells us how we can right our wrongs, how we can repent for our sins. It says you can add pound derive debug or manually implement debug. So I'll say like, oh, I'm sorry, compiler. I'll put debug back in, and it's happy again, and it will run again and compile again. Right? Same thing for equality, right? If I forgot to put in this equality, if I forgot to derive equality, the compiler is going to yell at me again because I try to compare these points, and then it says, implementation missing. I guess it doesn't specifically tell me to derive it, but I know that I can derive it, and I can just say partial EQ. There are cases in which you might not want to derive equality like this. So an example of this was like in CS 110 assignment 1, you had like Kevin Bacon or something like that, right? And then you have to like compare these movies, but you're not just comparing it like element wise based on the struct, like attribute wise on the struct. You kind of have to do something a little bit more complicated. Then you would actually manually define your own equality function. But what partial EQ does is it does the obvious thing. It'll just go element by element, and I'll see if they're equal to each other. Does that make sense to people? Double equal, sorry, what was the last one? Double equal in which one? So there, I don't believe I haven't seen a triple equals that seems to be specific to JavaScript. There's no triple equals in Rust. The difference here is that partial equal so if I had strict equality, that would mean that everything, it's just sort of like marking kind of like a logical fact about a type. I guess it's not really, I don't know if the compiler actually like verifies.
It's a little different. In most other languages, if you do double equals, that is checking for identity. It's checking if the identity of two objects are equal. So say you were to like create a list of numbers, and then you created another list of the same numbers, but it's a separate list. If you were to use double equals, say in Java, that would give you back false because the identity of those two lists is different. They are separate lists, even though they have the same contents. So in Java, for example, you would have to do list1 dot equals list2 to check if the values are equal. And that is what this is doing here. If you implement that partial EQ or EQ trait, it's checking are the values here equal to each other. And then when you use this double equal sign, you're checking is the value of this first variable equal to the value of the second variable.
So I'll give an example. So like for instance, like integers, I believe, if I recall correctly, in Rust. So the only difference, the only difference between partial equality and strict equality, like partial EQ and EQ in Rust, is that if something implements the trait EQ, that means that that like everything is equal to itself. Does that make sense? Everything is equal to itself. Floats do not implement that because not a number is not equal to not a number. Like the semantics of it are different. This is the only difference between the two. Does that make sense? Yeah, it's a weird technical thing, but the reason we had to do it here is because we wanted our points to have floats. Because in our next example, which we're going to transition to right now, we're going to talk about defining our own traits. So I'm going to do another screen share, another context switch.
Quick question about that example. Can you auto-define a display trait?
Auto-define, you can't. No, I tried to derive display and it was mad at me and it said I couldn't do it. I think you could do if you wanted to like do something simple, you could maybe like, you could derive debug and then you could like do like format bang with the debug in your definition of display. But I think the philosophy there is that, if you're showing something to a user, you should not just like derive it. Like you should be a little bit more thoughtful about how you're displaying it. This is more of a philosophical point of the language, I think. But that's a great question. Yeah. So when we're defining our own traits, say if, like we have this point and, like we want to describe things that have L2 norms. So in case you forget, L2 norm is like, if I have a vector, it's the length of the vector. Like if I have a point, it's the distance from the point to the origin. That's the definition of the L2 norm. Or if I have like a vec f64, maybe this is in a higher dimensional space. So maybe this is in 3-dimensional space or 10-dimensional space or something, right? Maybe we're using Rust to write some crazy physics simulation, right? So we're going to look at an example of how to define our own traits right here. So I'm going to stop share and I'm going to start share again. Again, please stop me at any points if you have any questions. But now we've got our same point. Okay, we've derived the same traits on it, and now there's this syntax for defining a trait. So just try to digest the syntax for a little bit. You say, trait is first of all trait. Here I just made this a pub trait in case we want to use this in other files or something, right? So this is trait compute norm, right? Compute norm is the name of the trait. Normally in Rust, it's customary to name your traits as verbs, very active, very vigorous, I guess, right? So because we're going to compute the norm, right? And then we'll define the function. So anything that implements compute norm has to define this function. So the funny thing here is that traits, when you're defining a trait, you can also give a default implementation. And this is kind of like my dumb default implementation. I'm going to say just return 0. So here, if I want to define a norm for an option of a U32, actually, so there might be a reasonable way to define this. Maybe I just return the U32 or something like that, and then cast it as a float. But I'm just gonna say, what's the norm of none? It's 0. It's the default. What's the norm of something, right? It's 0. So this will just inherit kind of this default implementation. And then so if we look down here, right? If I print, so here I have some option. So the norm of some option, I can call compute norm on it, and that will compile just fine. We'll just look at the output right here. So the norm of some option is 0 because it's using the default implementation. Do people have questions about that? Do people have questions about this highlighted portion of code here? I'm gonna pause. Okay. So then let's look at implementing kind of more reasonable things. So if I want to do it for point, what I would do is I would do self.x times self.x plus self.y times self.y, and I call the square root function on it, dot square root. This is how you compute square roots in Rust. You might be wondering, is there an infix way to do this? Can I have a square root function and define it around it? I think, let me just see if you can do, I think you might be able to do something float like f64 : square root, but it's just I've seen this syntax more often. I think there are also macros people have defined to be able to do infix computations and stuff like that, but we're not going to worry about that too much right now. Just think about this as the way that you compute square roots. So this is the square root of x squared plus y squared, the Pythagorean theorem tells us. And then if I have, so I should have actually displayed these before, but I had this thing called lil vec, or actually, sorry, yeah. So we had this point that had, I kind of conflated a bunch of examples here actually looking back on it, but let me actually just comment out a bunch of these, okay? Let me just make it much simpler. Let's say let p is equal to point new 3.0 comma 4.0. I have to put this 0.0 here to indicate that it's a float. If I say println bang the norm, the norm of this point, which I'm going to have the debugging format string, is this, right? I'll say p is, actually, sorry, I'm going to call it p2 so we don't have a name conflict. And then I'm going to do p2.compute norm. So what do you think this will output? Any guesses? Can someone just shout something out? What's the norm of 3, 4? It's our favorite Pythagorean triple. It's so catchy. What should this print? 5? Did somebody say 5? Great, yes. Lovely. Okay, so if we print this out, it's going to complain about some unused variables, but it prints out 5, right? So it prints out, because we derived debug, it will print out the point like that, and it says 5, which is great, right? So that's how that works. I'm going to comment this back in, because we'll see some more stuff soon. And then I can also implement compute norm for a vector of f64s. So this, I'm just doing this to showcase some of Rust's fancy functional syntax. If you're interested, we could devote lecture time to talk about functional Rust more. But I just sort of wanted to give you a taste of it here. You'll see definitely more with closures when we start talking about threads. But what we do is I'll define this iter. I'm going to map a function on it. I'm going to map this square function on it. And then I'm going to call this function called sum. So I'm going to do sum of f, and this is the f64 version of sum. I have to call it that way because it can't infer the type, unfortunately. So then I'll call sum on it, and then I'll compute square root on the sum. So this is like a very slick way to like define the L2 norm, and you'll see that that also works because I defined here a little vec of just 3.0 and 4.0, and it says the norm of a little vec is 5 right there. Any questions so far? I realize I'm going really fast. Okay. Okay, here's another really cool thing. You can use traits to override operators, which is super exciting. So if I impl add for points, what I can do, so let's just focus on, just digest this for a little bit. I can impl add for point, and I can say I'm going to define addition on myself with somebody else, and it's going to output something. It's going to output, so I don't think I talked about this capital self. This keyword capital S self is like, it's just a stand-in for point. Self just means like this type. Does that make sense to everybody? It's like the type of myself, right? Because the compiler is able to figure that out, right? And then we do it in the most logical, straightforward way. I'm going to define it as the output of the addition is going to be a new point where it's going to be self my x plus the other points x and my y plus the other points y. Does that make sense to everybody? And like I said, like you have links to the code in the slide, so you can feel free to like play around with it. Define, I think a great exercise would be define subtraction of points. What is like define a dot product for points maybe or something, right? And then, okay, another weird thing you might have noticed is this type output is equal to self. This is called an associated type. So this is kind of a little bit more of an advanced point, but what this means is that this addition operation, the trait definition, has to know what kind of type are you going to be returning, because it's not obvious that the output of an addition is going to be the same output as the two things that came into it. I'll give you an example for, I think it's easier to think about this for multiplication, right? So say I wanted to override the star, the asterisk for points to be the dot product, right? The output of the dot product between two things is not the same type as the input to the dot product. The input to a dot product is going to be like 2 points, 2 vectors, right? The output is going to be a scalar, right? In case you're not familiar with dot products, that's totally okay too. But it's in general, like we want to be, we don't want to restrict ourselves to outputting something that's the same type as the inputs. So that's why we have to define output. And here I said define type output is equal to self. I could have just as easily have written define type output is equal to point, and that will also happily compile. So if I do that, because like the Rust compiler will just sort of like figure that out, right? It happily compiles it. It knows what I mean, right? And then if you want to see an example of that in action, we can see in this last one, I can just do the origin plus point new 3, 4, and then compute the norm of that, and that should also return 5. As you can see, that happens right there. Are there any questions about that? So are there any, I'm going to highlight this code again. Are there any questions about this highlighted portion of code? Totally okay if there are questions about the type output equals point. I think that's weird. The way I like to think about this is like this output is kind of like a type variable, right? And I'm setting it to something in order to have the trait make sense. Any questions? I'm kind of worried about how silent it is, so I can't tell if people don't know what questions to ask or like if you want me to like rewind back to like a couple of slides before, that's also completely fine. So defining functions with, I see what you mean. Okay, yeah. So what's the benefit of, so that it sort of lets you group these types together in a way. And as we'll see soon, you can kind of like automatically define the trait for like a bunch of different types at once, right? So like say I wanted to like define a very general version of compute norm that could work on like a bunch of different numerical types or something, right? So like, yeah, so like I guess your question is like correct me if I'm wrong, but is it sort of like, why would I define my own trait when instead I could just do something like, I'm going to have an implementation. Instead of doing this, I'll just implement compute norm independently for point and independently for vector. Is that right? Is that your question, Julio? That's a great question. Yeah. So, it's useful to categorize our types in these ways because it lets us sort of define. So I can define, we'll see this with generics, which hopefully we have time to discuss in like the last 10 minutes here. If not, we'll definitely start there on Thursday. But like if I wanted to define a very generic function that says like print the norm or something like that, then I can like take in something of like a generic type that I can specify that the type that I take in has to implement compute norm, right? And that's useful, right? Because now I don't have to do like print norm for point and print norm for vec. I can just sort of write one function for a generic type, and I can specify that this type implements that trait. So I think, in order to properly answer your question, I think we'll have to see generics, and then maybe it'll start to make more sense there. If it doesn't, please ask it again, and then it might make more sense in that context. Do you want to mention something, Ryan?
Yeah, I think the simple answer to your question is yes. Like the point of using traits is to reduce the amount of code that you have to write so you can implement a function on a lot of different types. And it may be useful to compare and contrast this with object-oriented programming. Like the way that you reduce the amount of code that you write and avoid copying and pasting in object-oriented programming is you define a parent class, and then you have a lot of child classes inherit from that parent class. The problem with object-oriented programming is sometimes you end up with like inheritance hierarchies that aren't a simple tree. Like you don't have one parent class and then the child classes inherit cleanly from that parent class. Maybe in like half the classes you need to override a method in one way, but in half the other classes you need to override it in a different way. So then you're like, okay, well, let's create two child classes and then have things inherit from those child classes. But then sometimes you need to like slice things a different way, and it can become very complicated. I'll find a concrete example for you of when object-oriented programming kind of falls apart. This tries to take a similar approach where you're kind of sort of inheriting functionality in some cases, but it's a lot more flexible. You're not saying that there is like a single parent class with 10 functions that you inherit. You're saying we're going to slice that into a bunch of different traits, a bunch of different conceptual groups, and it's a lot more flexible and a lot more general.
Yeah, I think most people agree that like this way of like this is much more powerful than traditional object-oriented programming and like inheritance and how that works. But I think in order to fully appreciate it, it'll make sense to look at generics. So let's see if we can introduce that in the last couple minutes here. So I'm going to share my screen again. Yes, okay, generics. Here. Great. Can people see that? Okay. So you've seen them before, actually. You've been a client of generics before. Today we're going to learn how to actually implement them, right? So you've seen like vectors can have different types, boxes can have different types, options and results can work over different types. And soon in your weekly exercises, you're going to be upgrading the linked list from last week's lecture into a generic linked list, and you'll be implementing a bunch of like really fun traits on it. But now we're going to look at this link, this playground link. So I'm going to switch over again, right here. Great. Where we can define kind of like a struct using generics. So over here I've defined this matching pair. So it's basically just a struct that has two fields that have the same type. That's what the syntax here is saying. So the new things we notice here are these angled brackets, and there's this like t inside of it. So we're saying a matching pair of type t is a struct that contains first and second both have type t. I also defined sort of just like our own version of an option here. This is an enum in Rust, and what that means is that it's essentially of this type, or it's essentially going to look like something of type t, or it's going to look just like nothing, right? And then we can implement display for these particular, let's implement display just for like U32, right? So don't want to delve too much into the match statement syntax because we are in the last couple of minutes, and I want to like focus more on the conceptual points with generics. So maybe we can like revisit that on Thursday if we want to like delve more into match statement syntax. But Here you can just see that we're implementing how do we create a new matching pair. Well, I'll create a new matching pair by, it's just gonna, so I have this angle bracket t again, right? And it's saying I have to, my new function is going to take in something of type t and another thing of type t, and it's just going to spit out that struct, right? And then I can also implement display for a matching pair of type char in this way as well. Which is, so this is an example. So we can implement traits just like we saw with Vec F64 for a particular variance of matching pair. So here's an example. I can say like p's in a pod matching pair char is equal to matching pair new of p and p, and then we can print them out because we implemented display for them. And then in order to define my enum, I have to do like my option colon colon. This is the name of my enum, and this is like one variation of it. So if I print this all out, it will look like this. So 2 p's in a pod, and this is my sum of 5, and this is nothing. So let's actually focus like not on the enum, but just on this syntax. Does this syntax make sense to people? The idea that we can have a struct be generic like this, that I can sort of populate it with t. The whole point of that second enum there was just to show you that like option is something you could have defined yourself. It's actually a very kind of like simple definition once you understand enums there. But maybe we should talk about those on Thursday. Are there any questions about this highlighted portion of code and like what it means? So yeah, so this is how you define the generic struct. This is how you implement it. Notice how when you're implementing it, you still need that angle caret t. So this, like when you're doing the assignment, please come back to these examples, use them as a reference. Hopefully that will be helpful. So, and then kind of like a final word, I think it'll be good if we like ended on this note today. So we can actually have something called trait bounds. So this kind of goes back to Julio's question, I think. And we can do, so let's see. So I'm going to share this again. So if you'll notice, yes, great. So you see that? So in our previous example, notice how we implemented display for matching pair. So you see this highlighted portion of code. We implemented display for matching pair only for char, right? So like, what if I wanted to do something that had like a matching pair of like U32s, right? Well, I could copy it, right? And I could paste it, and I could, replace the char with like U32. And then it works, right? And then what if I also wanted it to work for strings, right? Okay, well, you tell me what to do. I'll just copy it, I'll paste it, and I'll, put string inside there, right? This should feel very wrong. Like you should be cringing, like when I'm doing this, right? Like this is the exact opposite of reusability, right? This is a horrible thing to do. But the magic of Rust traits is I can do something like this, right? I can do something like this right here. Where I can say, actually, let's not look at my option because we don't want to talk about enums, but I can say something like implement t, so I can implement like kind of this generic display for a matching pair of type t, where t is itself something that can display itself, right? And now this magically covers all of the cases, right? So I don't need to implement it individually for char or for string or for numbers, right? But I can have like, so I have matching pair char, I get 2 p's in a pod. I can also do let like 2's in a pod. I don't even know if that like, okay, I guess it's happy with it. The lecture is happy with it. I can say matching, this will be a matching pair of type, U32 is equal to matching pair new, it's just going to be 2 and 2, right? And then I can say, here, I'm just going to copy and paste this. I can print them out like this. I can say 2 2's in a pod is going to be 2's in a pod, right? And it just kind of knows what to do, right? So I can, invalid, okay, it's mad with how I named my variable, obviously, as it should be. It's a horrible name, never name your variable that. So if I do 2's in a pod, then that will work. Yes, exactly. Do you see that? So this is magical, right? Because Rust, I don't have to individually go through each type that can display itself and implement display for matching pair. I can just say implement it for all types that already have this display feature of them. Does that make sense? Does that answer your question, Julio, as to like why we would want to define our own traits maybe? That's a great question. If it doesn't have the display trait, so so that's basically saying, remember, I have a matching pair that contains two things that are of type T. If these two things don't know how to display themselves, then you know, then there might not be a logical way to display itself. But maybe I want to like still define a sort of like a default representation. So what I could do there is maybe I could have just like a more general thing where I can say implement here. Sorry, I'm just going to copy and paste this. So like just like, you know, if it doesn't implement display, then I can do, well, now I have to think of something that doesn't implement display. But then I can, where I just,
Vector.
huh?
Like vector, I think that doesn't
It
implement
doesn't?
display.
I think vector might, I'm not sure,
I think it implements the debug.
but not display.
I could be wrong.
Let me actually copy and paste the point that we had before because point doesn't. Some great live coding to see if this will work. So we have point. So I can have a matching pair of points. So if I have like this generic one where it shouldn't, so it might not be able to display itself, but it'll just say like, maybe it'll just like print out question marks, right? So I can just be like I don't know how to display myself, right? But if it does implement display, this will get overwritten. So let's just make sure that compiles by itself and that it's happy. Okay, so it's, let's see. Actually, it's actually angry because there might be conflicting implementations of trait display. First implementation here. Okay, I think I might actually have to like look into how you would like do like a default and override it with a trait bound. I don't know if you can override with trait bounds in this way, but like in general, you know, maybe there's a way you can like say a trait bound like that doesn't implement display. So maybe I think the question mark syntax, if I do like something like this, so it doesn't have to implement display, or sorry, maybe it needs format. Okay, actually, wait a second.
We can come back to
We'll
this.
come back to this
Thursday.
offline, I think. But yeah, but like in general, you wouldn't if the inside types can implement display, then probably the whole thing doesn't have like a logical way of implementing display. It's reasonable to think like how would we do like a default implementation for like less specific trait bound versions. But here the compiler is saying like, oh, you have these two different definitions of display. How do I know which one to use? So we'll get back to that question on Thursday. But that's a great question. Are there any other questions at the end of lecture? That's essentially what I'm trying to figure out. Maybe if we can say like where t, I guess this is technically after lecture, so we can just sort of like try it out. Where t, I think if you do like question mark format display, I've seen this question mark syntax before where it's like kind of optional. It says the default bound relaxes for a type parameter, but does nothing because the given bound is not a default. Only question mark sized is supported. So it could also just be that the Rust compiler might not be powerful enough to, I guess, define, to like give us this pattern, right? But that's something that I'll have to like do some more digging. I don't know if you can like say not, like you can like add traits together, but I don't know if you can like subtract them, so to speak. But that's a good question. Yeah. Any other questions? I guess, Warren, you still have your hand up? Or is that left over? Okay. I guess, yeah. Any other questions in general? Feel free to also like stick around afterwards and ask questions about any of the other parts. But yeah, we have a couple of other things. So like on the beginning of Thursday, I'll wrap up kind of this conversation here, and we can see an example in real systems code, and then we can talk a little bit about smart pointers. I can totally go over the match. Yes. Okay, so for the previous example, you're saying like right, let's see, where were we even doing that? Right here, you mean? Yeah, okay, so the match statement, you might have seen it in the context of error handling before. And what this means is I have a immutable reference to myself. I'm gonna match myself to, there are two possibilities, right? So if we look at the definition of this enum, have you heard of union types before, Brian? It's completely fine if you haven't. Like in like C and C++, there's this thing called a union, but it essentially means that this I'm defining a type called my option, and it has two variants. It has one variant that's something, and it contains a t, and it has another variant that's just nothing, right? And this is exactly like the option that you see in regular Rust. And what this syntax means is I'm going to try to, this is sort of like you're giving me this, so self is going to be this option type, and I'm going to try to match myself to this pattern. If I match with something, if I'm of this something variety, then I'm going to print this out to the console. If I'm of the other variety, then I'm just going to write this. And like, okay, yeah, so I guess delving into the syntax, you notice that we start out with these curly braces for the match statement, and then we have, the match statement consists of comma separated lines, or you can also make the right hand side of this like a set of curly braces too if you had a really complicated match statement. But on each of these lines, right, let's look at each of these items. On the left hand side, you have a pattern, right? So one possible pattern is like this is something containing num. And on the right hand side, we have the result, right? So you can think of match as sort of like a big, it's kind of like a big if else if statement where we're trying to find the pattern that matches whatever is here. And then the return value, so this match statement is actually, it's really cool because it has a return value. Just like an if statement in Rust, it has a return value. The return value is going to be basically the output of whatever is on the right hand side of this arrow. So right bang will return this format result. And it's very convenient that we define our match statement in this way because the return value of this match statement is essentially just going to be whatever the output of the successful branch is, right? So if it's going to be the output of writing this, or it's going to be the output of that. Does that answer your question? Do you have any other questions about the syntax? Exactly. So that's, yeah. So you have an example of that here. Do you see this highlighted piece of? So you actually can't say something. You have to say my option colon colon something to specify which, because we could have two different enums that both have something in them or something, right? So yeah, so you could say let my sum 5. It's my option U32. It's going to be my option something 5. This is how you use the syntax there in your code. Um, and this is much more powerful than enums in like C or C++ or Java because those are just integers under the hood. But this is type safe, right? You have like a, if you're like writing like OS code or kernel code and you wanted to define like, return codes or something like that, maybe it would make sense to have that be an enum, right? And then instead of just like some like random integer where like you might be able to like screw up the semantics of how that works. So like semantically, enums force you to think about your code differently, and that's good.
I think the difference between like C, Java, C++ enums and Rust enums is that Rust enums are a bit more like objects in that you can store things in them. Like you could have an enum in C that is something or none. But if it was something, you wouldn't be able to store an associated value with it. It would just be something. You couldn't like have something of 5. And you also wouldn't be able to declare methods on it.
No problem.